Afternoon, everybody. I think we'll get started right on time. So I'm really excited to introduce Professor Ria Kontou this week, visiting us all the way from Illinois. So Ria is a professor of civil and environmental engineering. Before that, she was at NREL, National Renewable Energy Labs. Before that, she did a PhD at the University of Florida, and she did a master's degree before that at Virginia Tech. And before that, you were doing an undergrad in Athens.
Right. Yeah.
And so currently she's involved with Transportation Research Board's Young Council.
Young Members Coordinating Council.
So any young people who are going to TRB,
yeah.
This is who you should speak
Please
to.
reach out.
She's also on the editorial board of Transportation Research Part C and D. She's a member of the Alternative Fuels Committee. And she does a lot of great transportation research, and particularly on electric vehicles, which is one of the reasons I thought she would be a great speaker for today. So I'll hand over to you.
Thanks, Scott. I appreciate it. I was really looking forward to coming in and talking to you today. The topic of my presentation is electric vehicle building Nexus, modeling charging infrastructure management in multi-unit dwellings and offices. This is a joint work with my PhD students, Rolling Zhang and Strachan Liu. We have collaborators at Argonne National Lab and Pacific Northwest National Lab. And portion of this work is funded by the Department of Energy, the Vehicle Technologies Office. However, not everything that I say represents necessarily the views of the agency. I'm going to start with an outline, brief background regarding my education experiences and the current research interests, and then jump into the community charging hubs management study and the techno-economic assessment of chargers in multi-unit dwellings. I'm going to focus on the motivation. So why do we study this topic? What is the challenge that we try to address? Then discuss the objectives, the modeling, and the application of our models in 3 big metropolises in the United States. I'm going to then shift gears, refer to the coupled electric vehicle and buildings, office buildings management schemes that we propose for efficiency gains, since with workplace charging, there's a lot of opportunities for coupled management. And then provide some concluding remarks. Hopefully this will leave enough time for questions and discussion. My research centers on the transportation and energy nexus, and my group models sustainable transportation systems and their management. Originally, I'm from Greece, so I got my diploma at the National Technical University in Athens, and then moved to Virginia Tech for my master's. Got my PhD at the University of Florida, where I also got to collaborate with Oak Ridge National Lab. Kind of got introduced to Department of Energy funded research and a lot of data-driven work. So I loved it enough to keep going in the national lab space, and I got my I get to do a postdoc at the National Renewable Energy Lab for 2 years, where I also realized that I am really eager to mentor young scholars, right? So I decided to find a way back to an academic space. I did research for a year at the University of North Carolina Chapel Hill before I actually landed my faculty position at the University of Illinois. And where I am very fortunate to advise this group of young scholars and mentor them. So this is kind of the most rewarding part of being a faculty member. When it comes to our research, we develop models, algorithms, and data-driven solutions to emerging mobility challenges, working towards enabling more sustainable transportation systems. We have 2 thrusts that we're mainly focusing on. The first one is related to electric vehicles infrastructure and charging management. We published recently a paper in Transportation Research Part C on evacuation route planning for alternative fuel vehicles. It's very timely nowadays with Hurricane Ian, thinking about electric vehicle evacuations and the reliance on public charging on the way to safety. We had another paper this year in Transportation Research Part D, focusing on allocation of investments, including incentives and charging infrastructure funding in order to meet emission reduction targets in a way that kind of spurs adoption, we found out that both rebates and charging infrastructure investments are needed. However, they kind of fit different market needs, right? Charging infrastructure primarily enables these long distance trips for frequent travelers, while rebates are more universally received from the population by discounting their high capital costs of purchasing an electric vehicle. We have a data analytics for sustainable transportation thrust. One indicator, kind of the research that we are doing in this space, is a paper that we published in Sustainable Cities and Society. We focus on quantifying transportation energy vulnerability. We adopt the social vulnerability perspective where we account for exposure to transportation energy burden, the sensitivity that different socio-demographics experience, as well as adaptive capacity to transportation energy fuel volatility. The last part is an energy policy paper where we focused on California vehicle rebate project investments towards rebates, and we showcased that policy interventions like income caps result in more equitable allocation of this incentive and adoption from more lower income and disadvantaged communities of electric vehicles. But enough with that kind of summary of the prior work. Let's jump into the topic of home charging. We see that policy making right now with the Infrastructure Act and the Inflation Reduction Act aims to drive adoption of electric vehicles and the deployment of public charging infrastructure, right? In many studies that are out there, research papers, the focus is public charging infrastructure deployment and modeling, right? And there's a lot of funding going into this. However, all of these studies usually tend to assume that home charging is ubiquitous and universal, whereas we see that there's a lot of property managers and homeowners that are worried about their capacity to deploy that infrastructure in place. And in a paper that we published in 2020, led by Dr. Green in Tier Part D, we utilized California Energy Commission data at that point to show that the majority of charging happens at home. Dr. Hartman also knows that from their study that 50 to 80% of the battery electric vehicle sessions occurred at home premise. Workplace charging comes second, and then public charging. So the most convenient place to charge and the most economic from the perspective of the payment and the electricity rate, the residential electricity rate, is home. Do everybody, considering the different housing types, have the same access to home charging or the capability to deploy and readily have chargers? The answer is no. We see from National Renewable Energy Lab data that only 2/3 of single-family housing type residents have the potential to install chargers. Lower share of apartment residents have garage access. You can see our supplementary analysis of American Housing Survey in the right-hand side, where we show that there are steep disparities in the share of garages in multi-unit dwellings and single-family homes, showcasing that there are still barriers in adoption of charging stations in these areas. There's also capital and installation cost burdens associated with potential electrical upgrades, which are also time-consuming. It can take a day or two to employ a level 2 charging station in a garage. There's also limited renter rights for those that do not own their home, as well as ineffective charging sharing practices and behaviors. Not everybody knows the etiquette of sharing a charger, right? So there is not centralized management and difficulty tackling the behavior of individuals when it comes to charging. Causal inference literature shows that limited access to reliable home charging infrastructure can hinder electric vehicle adoption and use. And thus, we go ahead with proposing the concept of multi-unit dwelling charging hubs. Imagine a parking lot in an apartment complex where we are going to have limited infrastructure resources. These are the charters that are going to be shared by a population of residents. We're going to do an analysis of centralized management of this type of system, scheduling sessions of electric vehicle drivers, and also calculate the levelized cost of charging through a techno-economic assessment process to support greater deployment of charging stations for renters and low-income communities. This is generally aligned with the funder's mission that we currently have to enable more equitable access to this type of infrastructure. The system looks like this. We have a multi-unit dwelling, an apartment complex, and its parking lot where we are going to have a limited number of chargers, and these will have to be used through a schedule by the electric vehicle drivers. The charging scheduling management scheme will enable efficient operation of the hub and also electric vehicle driver satisfaction with the experience of the system. Managing the system will take some optimization, and the outcome of this analysis is a power profile that actually describes the total energy of the system. And this will be fed into a techno-economic assessment using capital, operational costs, electricity rates, and the total volume of energy used through cash flow analysis in order to come up with a levelized cost of charging. What is the modeling that we employ? We use a job scheduling problem where this problem is able to determine the best sequence to process jobs on machines. We modify it. We rethink about the terminology jobs and machines, and we state that a charging session now is going to be a job and a charger a machine in order to come up with the optimal schedule of charging sessions on chargers. The objectives of this optimization will be the efficient operation of the hub and the electric vehicles drivers' satisfaction. We can capture these two by minimizing the make span. The make span is the time that elapses from the first session to the last session in the schedule. And it essentially, by minimizing it, we want to compact the schedule, the charging schedule in essence, right? Make sure that we utilize it as much as possible in the amount of time that we're going to go through. The second objective is minimizing the total waiting time responsive to the experience of the users of the charging infrastructure, okay? So in this setting, we still have people that are going to move their cars to a charging station, and thus we want to minimize the time that they wait in order to do so. This is also tied to the flexibility of having readily available any of the really close to your arrival time at home. Okay, we see that when we pursue our optimization, that the minimization of total waiting time, the objective function is much more sensitive there compared to minimizing the make span, and actually by minimizing the second, we are able to minimize the first. So I'm going to refer to the efficiency of operation of the hub with the term, with kind of capturing the minimization of the total waiting time. We have a set of constraints that we account for in our model. These are capturing the travel patterns of the electric vehicle owners, as well as their schedule constraints, okay? Of course, we have that every charger cannot be utilized by more than a vehicle at a certain time index, and that the ending time of a charging session needs to be at least as late as its arrival time and the time that it takes to charge. Note that the charging time, charging session has a different amount of time dependent on the power level of the charger, right? So if we charge at a level 2 station, it takes longer. The DC fast charging station, it's much faster. A charging session is only allowed on a charger after its previous charging session has ended, if it succeeds it. The thing is that modified job scheduling problem, it it's hard to solve for the scale of the problem that we want to address with using commercial solvers, Simplex and Kurobi. So we go ahead and propose a heuristic solution algorithm to be able to be responsive and also utilize the computational resources that we have in an efficient way. The inputs in this solution algorithm are tied to the charging session characteristics as well as the charger characteristics, while the outputs are related to the charging schedule. The solution algorithm has 3 modules. The first one is tied to preprocessing. We start with assigning charging sessions to stations, and we start with populating the slower rate chargers. This means that we're going to have those sessions that take longer in the beginning in order to leave a lot of the CFC open for later. The next module is tied to determining the sequence of charging sessions on chargers. We leverage 4 different dispatching rules. I'm going to expand on this concept in the next page. But the way that we approach this is as follows. We define the dispatching rules based on which we schedule the sessions sequentially on chargers. We run the charging scheduling simulation based on these dispatching rules. We note the performance, and we train a decision model based on the examples that we run so that we can create a decision tree that can enable us, based on the characteristics of the system, to propose the best dispatching rule. Okay, so we developed a decision tree using C4.5 algorithm, and we leverage the system parameters so that we can track the performance. These are tied to average charging sessions for a charger, average processing time of all charging sessions, average system utilization, etc. The last module is an improvement one, where we identify existing gaps in the schedule, and based on a set of rules that we have in the algorithm set up in our paper, we try to identify whether there are gaps where we can move certain sessions and further reduce the waiting time in this process. Okay, so based on the implementation of this solution algorithm, we can see that we can achieve significant gains compared to a first come, first served unmanaged charging approach. This is indicated with a blue line, the unmanaged one, and our algorithm results with the orange one. The benefits that we gain from the reduction of the total waiting time, which is the y-axis, are larger when the number of charging stations is smaller, because we have more opportunities to gain from the management, right? As the number of charging stations increase, we have diminishing returns from applying this algorithm, since more chargers are available to be used, and the charging management is not as effective. And this graph kind of pertains to a New York City multi-unit charging hub. We're going to see more details on that in a minute. An overview of the dispatching rules. These are tied to criteria on how we prioritize charging sessions on chargers. For example, we might choose to prioritize the session that has the earliest due date, or the shortest processing time, or longest processing time, or in a first come, first served basis. You can see in the picture right there 3 different electric vehicles that are going to share one charger. Based on their arrival time and due time and the charging duration that depends on the power level of the charger, we're going to deploy the dispatching rules and show how the sessions are going to be scheduled. If we prioritize the earliest due date, then the electric vehicle 2 that has the due time that's coming up promptly will be prioritized. Then electric vehicle 3 is the second one, and electric vehicle 1 the next. And in this assignment, we track the total system waiting time as 252 minutes. Whereas when we prioritize the shortest processing time, we see that an electric vehicle with a charging duration of 83 minutes is going to be first. Then the EV2 with 85 minutes, and then EV1 with 120. And this will lead to a total system waiting time of 259. Going through the longest processing time and first come, first served case, we see that the total system waiting time further increases. Thus, for this particular configuration of the system parameters, the earliest due date seems to provide the best results. All of these type of examples are given in a training example vector when we have system parameters and the best of the dispatching rules, and we train our decision tree in order to be able to provide insights to the manager on the dispatching rule that they should use based on the system parameters. Okay. This component enables us to come up with the performance of the system, right? So track the total waiting time that is kind of representative of the performance. Once again, the techno-economic assessment part is going to give us the cost of charging, essentially. We go ahead with discounted cash flow rate of return analysis with fixed internal rate of return and analysis period, financial inputs and capital and operational costs related to the charging infrastructure are accounted for. The electricity rates come from the utility of the region that we are focusing on, as well as the energy sold comes from the first component where we manage charging, okay? These all under the discounted cash flow rate of return analysis in order to compute the levelized cost of charging in this setting. There are three proposed business models that we are looking into. Let's see, the first one is tied to an ownership of residents of the charging hub, where you could have either apartment complex residents or a property manager or a homeowners association having invested in charging hub. These types of ownership would entail a residential electricity rate, which doesn't have a demand charge, so you only pay for the volumetric component of the bill, which is charged in dollars per kilowatt hour, and you don't pay for the dollars per kilowatt peak power use. This use case doesn't have any network or data contracts, comparing to a utility or private company use case. In a utility, we hypothesize that the charging hub is owned by a company that provides electricity to the premise already. And there exists network and data contracts, but the rate doesn't have a demand component. When in a private company, we have a commercial rate that has a demand charge, which can be a big portion of the electricity bill. And the station is owned by a charging station vendor, or it could be an automaker in a case of, let's say, superchargers, right? Or it could be an investor. The idea is that the techno-economic assessment and the charging management will be leveraged in order to understand for certain archetypes of multi-unit dwellings, the trade-offs between performance and levelized cost of charging. Okay, so here using American Housing Survey and National Household Travel Survey data, we developed these three archetypes for Chicago, Los Angeles, and New York City. Let's take the example of Chicago. The average multi-unit dwelling size has 9 apartments, 19 residents, and 14 vehicles. We hypothesize that there is universal adoption of electric vehicles in this setting. And if you notice, we have some bars, intervals of level 2 and direct current fast charging stations in the left-hand side of every subgraph, where we actually check, set the intervals of infrastructure that can be available for these multi-unit dwellings, in a sense that they will provide, cover the demand. So charging in these types of stations will be feasible and will not result in infeasibility, while also they will provide non-dominated solutions in our Pareto frontiers when we track the trade-offs between performance and levelized cost of charging. We continue with leveraging travel data in order to track multi-unit dwelling drivers' travel patterns. And we hypothesize that electric vehicle owners will keep having the same patterns as they currently do with using gasoline vehicles. We create the distributions of departure and arrival times, as well as the distributions of vehicle miles traveled. And we, with our collaboration with Argonne National Lab and Experian, we come up with a distribution of battery sizes in major cities so that we can address the heterogeneity of the sizes of batteries that there exist. We see that the most prevalent in all Chicago, New York City, and Los Angeles are batteries in the range of 55 to 65 kilowatt hours, and second, 85 to 95 ones. All this information is very useful because it enables us to create this synthetic data of multi-unit dwelling residents, travel patterns, and electric vehicle characteristics. In the use case of Chicago, having a definition of 3 alternative sizes of charging hubs helps. We don't want to recommend the optimal size. What we want, because we have conflicting objectives, 2 conflicting objectives, the total waiting time that tracks performance and the levelized cost of charging. But we go through this exercise so that we can demonstrate that we can choose a configuration with level 2 charging stations that have a total waiting time on average of 2 hours per vehicle, or we can have a large charging hub with no delay. However, the levelized cost of charging in dollars per kilowatt hour will differ. For the small charging hub, there is not a lot of heterogeneity across business model. We see that approximately the levelized cost is 15 cents per kilowatt hour. But as we move towards more efficient charging hubs, larger ones, we see that the cost increases. In the large charging hub case, we have 30 cents per kilowatt hour when the hub is owned by a private company. We see that the trend in this case is that as the business model shifts from residential to a private company, in a large charging hub, private company tends to have a larger levelized cost of charging. And this is because of the demand component that is part of the electricity bill in this setting. We produce similar analysis insights for Los Angeles and New York City. I think what's important to mention here is that in a small charging hub, lower performance based on the total waiting, since the total waiting time is bigger, we see lower levelized costs for private companies. And this is because based on the electricity rate, we can take advantage of this time of use structures that are available to commercial users. Think about the dollar per kilowatt hour pricing cost over the time of day being a stepwise function, and the tiers actually of difference in these steps enable us to gain more when charging happens during beneficial hours of day. And thus we end up seeing 24 cents per kilowatt hour in a small charging hub as the levelized cost of charging, which is smaller for a private company than a residential or a utility case. The results of New York City have the same trends as we've seen in LA. What's probably important to note by just going through back and forth LA and New York is that the magnitude of the levelized cost is higher in California, and this is driven by the higher electricity rates in dollars per kilowatt hour and dollar per kilowatt that are available in the region. So this also signifies that the pricing scheme, the electricity pricing scheme, is important in these use cases, and creating rates, designing rates is an important consideration for the business modeling of such charging hubs. Okay. These are the trade-offs essentially between the total waiting time and the levelized cost of charging. We present these for private company, utility, and residential in the 3 panels, while also we differentiate between the Chicago, Los Angeles, and New York City region. Note that all these points are generated for the same level of demand, right, with different sizes of charging hubs. As the color becomes lighter, we see more level 2 chargers being deployed. What we observe is that we have diminishing returns from the adoption of more and more level 2 chargers here, since the total waiting time reduces less as we deploy more and more chargers. Another interesting kind of insight that stands out is that the LA costs are significantly higher than New York City and Chicago. We discussed about the importance of the electricity rate in this space. Generally, we see that levelized charging cost for a private company is greater than the same costs for either utility or residential station ownership. We also create the same type of curves, but for a variety of configurations of chargers. So we might have not only level 2, but combinations of level 2 and direct current fast charging stations. And we are actually able to capture trade-offs dependent on the sizing there. Similar results when only direct current fast charging stations are there. As more stations are deployed, the total waiting time decreases, the levelized cost of charging increases. There's diminishing returns from deploying more DCFC in general, and we are able to capture that here. Perhaps what kind of helps us put everything into perspective is that if we aim, for instance, to minimize delay, right? So we say that we want a charging station configuration with 0 delay. It would be better for us to choose a configuration with 2 DCFC and 22 level 2 charging stations that will result in 36 cents per kilowatt hour levelized cost. And if we are interested in a levelized cost of charging of 35 cents per kilowatt hour, then a configuration with 2 direct current fast charging stations and 20 level 2 stations will give us on average 7 minutes of delay per vehicle, which is very good. So we are able to make these comparisons and provide pointers to potential investors in this space. The insights that we derive from this analysis are related to quantifying these trade-offs between performance of the system and the cost of charging for the same level of demand, as well as solutions for charging power level alternatives in this space. This is a collaboration with our Argo National Lab collaborators, essentially researchers in the space. And we have insights from the Chicago Area Clean Cities Coalition and the Illinois Department of Transportation, who are very interested in the Chicago application, actually. I'm gonna switch gears a little bit. Remember that in the motivation, I highlighted the fact that workplace charging is actually the second most prevalent premise, right? We see a lot of opportunities for deployment of chargers there, not only for the drivers who might lack reliable home charging or might experience range anxiety, but also because they can help achieve corporate sustainability goals and they can help attract employees and tenants. So this is a big selling point for corporations. The thing is that we can consider coupled system of electric vehicles that are co-located in parking lots of offices, right? And this means that there are opportunities for management across the building and the transportation space for their energy use. We can employ building control strategies that stem from thermostat set point adjustments or daylighting control in the office buildings that could help reduce the amount of energy in the building. We can come up with an assessment through building simulations in different US climates using E+. Actually, this is our collaborators work from PNL that are experts in building energy systems. And we are complementing this analysis with our electric vehicle charging management. In this space, we have knowledge of the commuting patterns and the travel needs of the electric vehicle drivers, first of all, we can compute the amount of electric vehicles that can be facilitated at an office parking lot and can actually take up the energy use that was saved from the building control strategy so that we can add one more load to the building without increasing its total energy use. And then we can manage this flexible load, the electric vehicles, in order to further reduce electricity bills and take advantage of time of use electricity pricing. Okay, so this is the idea of how electric vehicle charging management plays a role here. At the end of the day, we have this electric vehicle and building nexus, where we have efficient building energy use because we reduce the total energy use of our building. We account for this reduction in terms of the amount of EVs that can now be hosted in the parking lot. And then we can tackle this flexible load, manage it in order to reduce our electricity bills. In this setting, for 3 different cities, Chicago, Baltimore, and Houston, that have all, I should say, a little bit of different climates in terms of the temperatures that people experience in these locations. These are the results for summer type modeling. So the adjustments in the building's thermostat temperature set point is from 24 degrees Celsius to 26, with a step of 0.5 Celsius in summer period. We can see that, for example, in the region of Chicago, we can save with a 0.5 adjustment of degrees Celsius, approximately 50 kilowatt hours. And these can be leveraged in order to charge 7 electric vehicles, right? So we can see the equivalence there. Of course, this is taking into consideration the travel patterns of and the differences across these locations. Then with the daylighting control, which is shown in the lower panel, we can calculate the contribution of daylight and beams of electric lighting to meet a target illuminance level of 300 and 500 lux. For 500 lux, which is more moderate target illuminance level, the savings can be big. So 240 kilowatt hours, but can correspond in Chicago to approximately 35 vehicles. Okay, so this is kind of an equivalence of how many EVs can be hosted after implementing the building control strategies. We mentioned that this is a good opportunity to manage the charging in this space. We can do so in any of these scenarios. I think I provide some insights about the 0.5 and the 2 degrees HVAC set point adjustments. We can see that when we host a limited number of EVs, the opportunities there are smaller in terms of the management, right? So the reduction in the peak is evident, but not as large as when we host more vehicles as expected. The maximum peak difference in the 0.5 degrees Celsius adjustment is 19.8 kilowatt in Chicago and 26.4 kilowatt in Baltimore and Houston. The amount of peak load differences decrease significantly in the +2 Celsius degrees in the HVAC point adjustment, particularly for the region of Houston during summer. There is also benefits that are accrued from the electricity bill reductions. In Chicago, for a commercial use case where we don't have demand charges as a portion of the bill, so we're not getting charged based on our peak demand at this setting. The cost savings from the building set point adjustment can cover the cost of EV charging. And in Baltimore and Houston, where we have a demand charging component, we are able to even further reduce our electricity bills by charging management. In this setting, the higher electricity bills can be driven by the demand charge, which is impacted by the ratio of the number of EVs to the number of chargers. This is an assumption that we have to have baked in every analysis. And it's also an indicator here. I would say that a few of the conclusions, we have a lot more analysis for numerous cities across the US, that electric vehicle charging management is useful to reducing the total energy costs in this setting and managing EVs. And of course, when we have electricity pricing, electricity rates that are designed properly, we can save more by charging during off-peak hours. And when the coincident period of low electricity prices and dwell times are occurring, right, then managed charging schedule is becoming much more effective in the setting. That's all that I had for you today. Please let me know if you have any questions. I'm happy to start any discussion at these points.
At the back, Peter.
That was a few questions. I'll start with one. When you did the levelized cost of charging, you have this the IRR.
Mm-hmm.
Is that a same IRR for residential, residential, private, and commercial?
No, not really.
Okay, that's what I wanted to make sure. What?
Yeah.
They're very different.
No, not really. This is in accordance with the business model
Right.
in our techno-economics. Yes.
And then the second is when, what I guess, I've done EV charging, like, I can't think of an instance when like a multi-unit dwelling, like, I want to install a DC fast charging.
Mhm.
It's like way too expensive, like, it's just not economically feasible.
Mhm.
And I'm curious why you included that in there. Like, what are the costs for DCFC? You know, for a small multifamily, like
Mhm.
mom and pop owned, they're not going to do that. Like maybe a large one, maybe like a large portfolio, equity residential, things like that. They might, but like, I'm just curious why that was included and what are the costs that are using it.
Sure. Thank you for the question. It's great to be given the opportunity to elaborate. So the capital costs are also included in the levelized cost of charging. And yes, it is an overkill sometimes to think about DCFC offered in a multi-unit dwelling. But our next portion of the analysis is thinking about home charging primarily happens at night. What if we have utilization of the charging stations during the day? In areas with mixed land use where these lots can be leveraged by those that are traveling in the city to go to their place of work. So this is an additional portion of our analysis that will expand the power profiles and the energy use in the setting, and they will hopefully result in more economic use cases for direct current fast charging in these settings. You're right, the majority of multi-unit dwelling charging right now refers to level 1 and level 2 when we have a lot of residents. But DCFC was explored because we had in mind that we can use these lots for other purposes like charging of fleets in these mixed land use urban areas.
I might have missed this, but what are like the assumptions the model takes into account about the vehicles moving after they're done charging? I imagine like the results would be different if the vehicle was done charging, let's say 3 p.m. but didn't move until 5. Like, what are the assumptions for that?
Yeah, the assumptions are related to every single occupant knows their schedule that is coming from the centralized management, so they will have to experience this inconvenience of moving their vehicle. But yeah, if you hypothesize that these vehicles are autonomous, right, they could move quickly, or if they have such an automation feature. However, right now, this is an inconvenience that people are facing, and this is part of our definition of performance of the system, accounting for their waiting time. Usually, home charging happens as fast as you go home from work, you tend to recharge, or depending on your pricing scheme from the electricity provider that you have, you may wait. However, in this use case, the assumption is that you will wait until you're called from the management scheme to go ahead and charge.
Have you run the model with like the autonomous like scenario? Well, I'm wondering whether
It wouldn't
results
be
very different.
different from the results that we currently have, but you might need to consider. Then the waiting time wouldn't really worry the EV owners that much, since they could do other activities. We have a different study on all the behavioral preferences in this space, because dwell time at home tends to be large, right? So you have maybe 10 hours having your vehicle at night staying in your garage. So you have a lot of flexibility, and you can move your vehicle charging at any point during this period. However, as you mentioned, there is this inconvenience of getting up at 3 a.m. and then plugging in your vehicle. Theoretically, in a system where you have a person kind of monitoring your garage, this can happen. But yeah, it's a good question on how exactly the operation kind of favors connected autonomous vehicles versus human-driven.
Or autonomous chargers, right?
Uh-huh,
The chargers
yeah.
can move around.
Yeah, the charger could be autonomous.
I don't remember who's next. Maybe Kelly.
So I may have also missed this, but are the hubs like replacing parking for conventional vehicles? And then if so, like it would probably differ by cities, but like is there analysis on how like that could increase competition for like off-street parking? And I think that's another reason why, yeah, I probably have more to say, but like why apartment owners wouldn't want to like penalize conventional vehicle owners. So
Yeah, that's a good question. I think it ties back to the expansion of this analysis that we have laid out for the future. When it comes to the parking spots, right? Here we assume universal electrification, so all the residents own electric vehicles, and essentially during nighttime, where the majority of these operations happen, because it's home charging, right? There is no competition from other drivers who come to park, but this might play a role in a parking lot where you have a variety of users who have heterogeneous durations, right? They don't usually stay just for 8 or 10 hours at night, but they could come in and charge and leave, or they could park longer there. So yeah, you're absolutely right. There's a lot of practices that are discussed in the literature regarding parking management. Through pricing, you can kind of address issues related to why would somebody prefer parking there versus curb parking, etc. Yeah, that's a good question. We are trying to investigate this with the use of multi-unit dwelling charging hubs for other purposes.
At the back by the TV.
So couple of things and then my actual question. So I think the answer to the one about the plugging in and out really has to be in the design of the system. And essentially, if a lot, and coming from a civil engineering perspective, right? If a lot is designed so that all of these vehicles are coming in and parking at the same time, and it's just turning on and off to whichever vehicle is charging at that point in time, you've essentially solved your problem without anything having to move anywhere, right? So it's just the design of the system itself. Second point is, I love to hear what you said about the next is sort of the land use piece of this, because I think in these residential settings, really the answer is these charging stations where it's being used all day, and we're being smart about land use so that our EV charging capabilities are being paired with making sure we're being multi-use in our development. And there's good outcomes of that. Hopefully we won't ever use these vehicles. They'll all stay fully charged because we can just walk where we want to go. My question though is, how do the scenarios change? And this was a wake up moment for me moving to Davis, was how prevalent solar is. And I've started to look at the projections And that totally changes the dynamic of the nighttime charging because the solar is daytime. And so all of this point about residential being a preference, I feel like that goes away when we hit 20 and 30% solar.
Yeah, you're absolutely right. Thanks for this question. Right now, a lot of the pricing schemes actually incentivize charging at night and avoiding, not actually at night, but let's say after 9 p.m. and usually the peak pricing starts around 2 p.m. Till late in the evening. So the design of electricity rates becomes a very, very important point from that point onward in driving charging behavior, right? So the users will be responsive to these charging prices through their electricity time of use rates. Yeah, I totally agree with you. Solar can, over the day, can reduce pricing and also can be a more environmentally friendly option. This would be a very good application for the workplace charging use case. So yeah, I think we are trying to tackle all of these problems, thinking about the different premises and areas where charging can be facilitated. But you're absolutely right. Electricity pricing, the integration of renewables, all of these needs to be thought out in the future as we have more and more EVs being adopted.
Yeah, I just wanted to go off something we were talking about with the curb parking. I know we were essentially considering that everyone has 100% EVs, but does the model consider like curb parking in denser, older neighborhoods where there's like little to no lots or even like garages where the majority of users are parking and competing for curb parking?
No, not really. Yeah,
Okay.
curb parking is not really introduced in this model. It's pretty much relevant to multi-unit dwellings that have a limited parking lot, and installation of chargers can be pursued there. So kind of the use of the parking lot is for the residents, essentially. The model could be extended from the management perspective to account for other schedules, but it wouldn't be responsive to any competition in terms of that you would experience in a curb use case.
Yeah, so going off of what you had proposed about like switching on and off different chargers, where like how much of the levelized cost is the like actual upgrade of the main feeder and the transformer in order to add along these chargers, and how much does that like the like electrical code I think is written in a way that like every single additional charger used, they assume like some very large diversity factor in order to like that adds to like the size of your transformer and your main feeder. So like, is there a way that you can couple this with like revising the electrical code so that in multifamily dwellings they can like still build like a port for every spot, but not actually use all of the parts? Is that a consideration?
Yeah, I think this is a policy kind of consideration as well. Now we did not take into account. Okay, so in the techno-economic assessment, yes, there is accountability for upgrades needed. I think I need to dig into the numbers in order to give you a more comprehensive answer there. But yeah, based on the utility setting, right, and the needs for upgrades, we can have slightly different numbers. We tackled this in the sensitivity analysis that we've done on top of everything, but I'm happy to give you more specific numbers on the assumptions. Unfortunately, I don't have an exact answer for the portion of the levelized cost that is attributed to the capital costs, but I can give you more pointers.
Thanks.
Similar question, but in terms of how you are going to price questions on the preferences of people in terms of maybe if they're like if they book in advance and they arrive on time, will they get a discount for the time they are charging, or in the contrary, if somebody stayed longer than they were supposed to, will they get a fee?
And also, how do you like actually change the current model of pricing per kilowatt in like a normal charging station to adapt it to this new like setting where like a different kind of manager in every place has to have like, according to their price and stuff. So that's it.
Yeah, I think what we're suggesting, if I understand correctly, is a reservation system, right? Yeah, I think this is also a prevalent practice in parking management in general, where you have a reservation fee and then your parking fee that can be time dependent, right, and varying. And you can have a rolling horizon in this case. This is exactly what we are trying to do in our next step. Yeah, you're kind of proactive seeing the next portion of our analysis in there.
So I think this concept of having managed parking operations is very interesting, and clearly your model has demonstrated that that's probably the way that these sort of multi-use dwellings can help them save a little bit of money by not having to invest in as many chargers. And I'm just kind of curious from the kind of a high level how you think the operations of this kind of management would ideally work. So this is just a big question. You don't have to have a complete answer to it. But then another one is, have you considered including in the model the cost of waiting? So right now you have kind of two trade-offs. One of them is waiting time. The other one is cost. But of course, if you have a economic preference for how much it costs you to wait, then you can combine those, and then it just becomes one levelized cost in a sense.
Yeah, okay, I see. So let me tackle the second question, which I remember clearly. First, yeah, first of all, the time of wait can be monetized, right? So we can put a price to it. So if it's linear, then it's all right. It might be non-linear based on income, things like this, but we can still tackle that through this analysis. Yeah, then your first question was related to management at scale.
Yeah, like just like for like an apartment building, let's just say, like how do you imagine this might work, or in a condo, for example, how do you see this kind of management system work? You don't have to have a complete answer. But
yeah. The idea of the system is pretty much that at the beginning of the day, knowing in advance your schedule, central manager runs this optimization and tells you that based on your constraints that you have provided, right, and your recharging needs, and based on the station that we're going to assign you, whether that is a fast or a slower one, this is your schedule, right? So the idea will be that the residents will be responsive to the centralized management and follow it, given that they have to share these limited resources. Now, there are other types of schemes that are driving the behavior, nudging the behavior through pricing, right? Where you actually can reserve a space by paying, and if there is enough demand for this location, then you will have to pay more, right? So there are other practices that are prevalent in public charging lots, in public parking lots. I'm not sure whether there are reservation systems for chargers, but that might be a case as well. Yeah, so the idea here would be centralized management, day ahead kind of schedule, and provision of the schedule in advance. There could be more dynamic applications of this case study, but it was not examined in this analysis.
We want to take your study to the policy paper. And this is optimizing behavior. Your last example was great. So we can solve most of the congestions on the road by telling every person what time to leave home, what time to leave work, just managing every one of us with a centralized computer that will manage all of us. And that's what you suggested that we will do with the charging, but it's not very realistic. So what do we tell the policymakers as a result of your study? How to move on?
Yeah, I don't know if it's not so realistic in a residential parking lot. In an IKEA parking lot, yeah, it wouldn't be realistic at all, or in a in a downtown parking lot, but yeah, I think it's definitely not in accordance with economic nudges type of thinking, right? I agree with you on that. Let's see. So the idea would be that policymakers could take a closer look on the system optimized analysis, right? And see what could be achieved in this use case, and could go back and come up with electricity pricing schemes that could incentivize and nudge behavior to be responsive to that, or other types of nudges that might not entail pricing, where people can actually be responsive. I would also think that from our analysis, one big take is that we have the opportunity now to couple energy uses across residential, commercial, and parking lots. And because these tend to be attributed to a single payer, whether this is a property manager or the workplace property owner or the corporation that owns it, there are opportunities to further take advantage of the electricity loads that are more flexible with appropriate nudging and behavior incentivization.
Thank you. Thank you for your presentation. I like three-part but simple ones. You started explaining, you were saying you're accounting for transportation energy burden and for the capacity to adapt people. And based on the more strict rules and based on an economic system where offer and demand, it's high demand, you know, it kind of seems like it will gentrify areas even more. Have you accounted for maybe polarizing, you know, poverty?
Yeah, that's a good question. Not really. The study, we didn't really look into the lenses of equity here. Was that this type of premises, like the multi-unit dwellings, do not really have provision right now for charging. And because in multi-unit dwellings and apartment complexes, we see more lower income population residing in the majority of the cities, as well as renters who might not have the capability to go ahead and install their own infrastructure. This is kind of the equity lens that we attribute to it. But you're right, there are other effects that are attributed to the ways that these benefits that are offered to multi-unit dwelling residents can affect who actually gets to live there.
So as a follow-up, yeah, there could be a consideration that subsidizes to certain populations or.
I think that's really fair. What you're suggesting is investing in these premises where populations that are disadvantaged reside, so that they will have the opportunity to charge and potentially make some money out of it if they offer these lots to the general public over the day.
How do you account for transportation energy burden and capacity to adapt?
Okay, so this is a different study that we've done. This year. It was published a year ago. We conducted it. There is this lag between finishing research and getting it published. So in the energy vulnerability study, we accounted for energy burden as the share of the income that is spent towards transportation expenses. And the sensitivity of populations is attributed to who experiences energy poverty. We have a lot of background studies existing in the literature on those that, for example, have small kids or elderly households get to experience higher levels of residential energy burden. So we are accounted for these types of populations that we've seen in the past being more sensitive. And the adaptive capacity was captured as access to other modes. So shifting away from automobility, right? Thinking about access to transit and reliable transit, and the opportunities to reduce fuel costs for transportation through taking these modes.
I was just thinking, like while we were talking about autonomous chargers or upgrading capital costs to plug every vehicle, you know, aren't a lot of tools. It might also be more cost effective to just hire someone to manage the charging. Do you think, well, like, do you have thoughts about incorporating that maybe into?
Yeah, I don't think that we've thought about that. It might be a service actually in certain high-end luxury apartment complexes, so it might not be that far off. But no, this was not taken into consideration. I would imagine that this would entail some labor costs. Yeah, I don't really know how this would impact the levelized cost of charging.
There are like workplaces in the Bay Area like that have valet managed charging. So kind of exists, but it just sounds expensive. Yeah. Julia?
Assumptions you have mentioned called the next one. Which is like the total amount of time that the initial. Yeah. Consider that the battery has to be charged, or is it also maybe initial preferences of the users?
That's an excellent question. So the idea is that the users, okay, so what happens from the historical data that we've observed is that electric vehicle drivers who have vehicles with longer ranges do not necessarily need to recharge every day. So in this analysis, the amount of charge has to do with the amount of commuting the previous day and all the other travel purposes, right? So it's pretty much driven not by necessarily not by necessarily charging a full battery, but accounting for the travel patterns of the electric vehicle owners. There is some stochasticity in terms of the examples that we generate and we train our model with respect to the beginning state of charge, the state of charge at the beginning of the day. And yeah, the assumption is that we go up to 85% or 90% state of charge because the time that it takes to charge based on your relationship with your state of charge is nonlinear, right? So it takes a lot of time to go this last 10%. So we try to avoid that.
And what do you do
in the event of a
true vehicles?
Oh, okay. So this is random. So we don't really. I don't think that we really have a rule for that. It also okay. So it depends on the dispatching rule, right? Because some dispatching rules, it also matters the earliest due time, right? So you can have two vehicles arriving at the same time if your dispatching rule is like earlier arrival. Time, prioritize this session, then you can randomly choose between them. If your dispatching rule is earlier due date, then you're gonna also take a closer look on the amount of time that a charging session takes.
Benefits of the system, cost and the reduction of the wait time, you also consider what fairness in the sense of, for example,
there has like larger battery size. According to the specification of time, battery or something like this. And yeah.
Yeah, that's a good suggestion. So based on what I understood of your point is that person that has a vehicle that has a larger driving range, then yeah, I guess there is a fairness component related. So if based on the dispatching rule we prioritize them, right? Then somebody else they will be able to maintain their flexibility even though they might not need it, right? Depending on the schedule. Yeah, I think that's a fair point. I am not sure how to necessarily address it in this setting. You would probably need to know beyond their battery range, their future driving patterns down the road, right? So, and also their access to other charging stations. Yeah, that's a good suggestion. We have a study that we taken a closer look into like preferences for charging behaviors, and one of the components is tied to how flexible my schedule remains, right, based on my assignment to a specific slot, right? If I am assigned to charge and I finish my charge just before I go to work, right, then I don't have a lot of flexibility there. And people can be generally risk averse in not being able to utilize their vehicle. So we have an upcoming study where we compare and contrast this type of potential issues with this approach.
I think I missed it, but how did you consider the uncertainty on the charging site and charging infrastructure? And are you using a dynamic optimizations because you have a charging reliability and charger may not are available at that point? And how your model updates itself after and the business plan after it understand that the charger is not available at that point?
Okay, so good question. This is a time index model, but it doesn't really update in time. We have prior knowledge of the schedules, right? For working days, this might be relatively a good assumption. So there is not, there is knowledge of the demand in advance. Let me put it like this. Then your question was related to the optimization scheme. So once we have knowledge of the demand, there is no concern. We pretty much know at every time of day the demand needs, their scheduling constraints, right? And every analysis is run for a specific configuration, right? So the demand stays the same across all the analysis scenarios that I've showed you, but the number of chargers and their composition, their different levels vary. So think about every optimization being run for every configuration.
So you did not consider the uncertainty of the demand?
No. This comes, there are synthetic data that come from the distributions that I showed you, but there isn't really uncertainty in there is kind of deterministic knowledge of the demand.
So because based on our studies, the behavior of the drivers change every day. And when we use a constant or the constant distribution, it could be misleading because, for example, Tuesday, Wednesday, Thursday, maybe have a completely different charging demand.
Yeah, you're right. The analysis is run on the daily basis, but hypothetically, given a day ahead schedule, we could run this optimization and be ready to provide insights. But yeah, you would need a much more dynamic model in order to address uncertainties of that level.
A lot of great questions, everyone. If there's nothing else, let's thank Ria again. Thanks a lot.